Is everybody everybody in a place where I can take over your computer screens for the lab? Okay, I'm doing it. See it? Two. What the? Formation thing. Singing Hell Carnation Monkey Skunk. I'll let you guys read through the summary of theory and stuff on your own time. I'm just going to get straight to the procedure. Set the signal generator for a 1 volt peak to peak sine wave at a frequency of 1.25 thousand hertz. 1 volt peak to peak. Is that the same one you were using last time? You let your parts get home too. Yeah. If you guys come here with an idea. There you go. All right, so what, back to our procedure, what was it? Set the function generator to what? 1 volt peak to peak and some 1.25 kilohertz. Okay. Amplitude, channel 1. Oh, 1, 2, 5 kilohertz. That's my frequency. We'll go down to amplitude. And go 1 volt peak to peak. So my 1 volt peak to peak, 1.25 kilohertz. Set the oscilloscope seconds per division control to 0.1 milliseconds per division. Okay, channel 1. I'm at 1.0 milliseconds. 0.1 milliseconds per division. Right. So that'd be 100 microseconds. So 100 US, 100 microseconds per division. The expected time for one cycle or the period is the reciprocal of 1.25 kilohertz, which is 0.8 milliseconds. Okay. With the seconds per division control at 0.1 milliseconds per division, one cycle requires 8 divisions across the screen. This is presented as an example in line 1 of table 16-1. So down here on this table, we compute the period, 0.8 milliseconds, 0.1 milliseconds per division, number of divisions needed, measured period. Okay, change the signal generated to each frequency as listed in table 16-1. Complete the table by computing the expected period and then measuring the period with the oscilloscope. Adjust the seconds per division control to show between 1 and 2 cycles across the screen for each frequency. Well, I'm going to go ahead and hook up the function generator right to channel 1, which I've got displayed. It should be able to count the divisions and match up the information they put in that table to our stuff. This is my oscilloscope or my function generator, and this is my oscilloscope channel 1. Positive to positive, negative to negative. Turn channel output 1 on. Whoa, whoa, whoa. Anybody else getting this? Huh? Do I have mine set up right? Amplitude 1 volt peak to peak. Frequency 1.25 kilohertz. My seconds per division is 100 microseconds. There it is. Oh, oh. Ring looks a little better at 500 microseconds per division. This. That. Ooh. 100 microseconds per division. 200 millivolts. Are you guys seeing this, or what are you seeing? Do me a favor, hit the, this is kind of the miracle button, auto set, and that your function, your scope will read a signal coming in and try and display the best picture it can. When you do that, you probably will see something like this, right? Okay, so once I did that, I changed the milliseconds per division back to, what was it, 100 microseconds? And I got a sine wave that looks like this. Okay, so using that, let's look at the table here. It says 1.25 kilohertz. That's a generator on the frequency, or on the, that's a frequency on the signal generator. Computed period. How do we do that? Remember the formula for period? T equals 1 over the frequency. So 1 divided by 1,250 equals anybody got a calculator with them? 1 divided by 1,250. 0.0008 seconds, or 0.8 milliseconds, right? And if our oscilloscope seconds per division is set to 0.1 milliseconds per division, the number of divisions we would expect to see for that one period or that one cycle is 8 divisions. Everybody understand that? So on my scope, it says 100 microseconds, but that's the same as 0.1 milliseconds per division, right? So now if I count the number of divisions it takes, and I can do that by adjusting this horizontal position button. And what I want to do is get one of these alternations to line up with one vertical line. So I'm going to move this over to the left so I can count the number of divisions, right? I've just put it on this little hash mark here, and I've got one whole period, one whole cycle. I can count the number of divisions. 1, 2, 3, 4, 5, 6, 7, 8. 8 divisions. So that's this number. So the measured period would be 0.8 milliseconds. Right? Because 0.1 milliseconds per division times 8 divisions equals 0.1. 0.8 divisions cancel. I'm left with milliseconds, 0.8 milliseconds. And that's where they got that number. Is that driving in everybody's brain? Basically, in this column, we've got two theory of vision. We don't really care what that is. All we care about is we get 100 man. So we want to get 100 life that's the same as saying. That would should. Scale. I use this horizontal position. This line up is 0.1 milliseconds per division. We're counting how we're measuring how far this way the cycle is. Right? So each division represents. Now we're measuring horizontal. Okay? That's how they came up with that information. All right, I'm gonna go through the 1.9 kilohertz row with you, and then I'll let you do the rest of the table. So we've got 1.9 kilohertz. Let's compute the period. What's that formula again? So 1 divided by 1,900. I'm getting 0.000526. So how many milliseconds per division is, or milliseconds is that? 0.53, yep, 0.53 milliseconds. Now I'm going to change on my signal generator, I'm going to change the frequency to 1.9 kilohertz. So I'm going to go to frequency. So now my frequency doodad is lit up. And right here, where it says 1.25, I'm going to change that to 1.90. 1.9. 1.9 kilohertz. So I'm at 1.9000 kilohertz. And my output is still on. One volt peak to peak. So my oscilloscope now, I'm still set at 100 microseconds per division, which is the same as 0.1 milliseconds per division, right? And with the sine wave, exactly how it sits, can I still count the number of divisions? Yeah. If it looked like that, I would have to adjust it, right? So I'm still at 0.1 milliseconds per division. As long as you can see the a full cycle. Remember, we're counting horizontally. We have to have a full cycle or a full period in that screen. As long as we can count the divisions. No, horizontally, we're going to adjust milliseconds per division this way. This adjusts horizontally. Right, can I count it this, can I count the divisions this way?
Yeah.
Okay, well, let's do that for an example, okay? So right now, I can count one full cycle, right? But my milliseconds per division is 50 microseconds. So I'm gonna write that on the table as, how many is 50 microseconds? It's 0.05 milliseconds, right? 0.05 milliseconds per division. Now I can count my divisions. 1, 2, 3, 4, 5 point, I'm going to say 5.25 divisions. So how do I get my measured period? That's going to be milliseconds per division times divisions. So 0.05 milliseconds per division times 5.25 divisions. That cancels, and what I'm left with is 0.05 times 5.25 equals 0.2625 . 0.2625 milliseconds. Is that right? This number should match up with that, but I'm getting about half of it. Why is that? One divided by the frequency of 1,900 is 0.53 milliseconds, okay? My oscilloscope seconds per division is 0.05 milliseconds per division. 50 microseconds is 0.05 milliseconds per division. Per division. 1, 2, 3, 4. Oh, I only counted half of my. Why didn't anybody catch me do that? So this is wrong. I counted half. Everybody see that? What I did wrong? I counted the top part. I didn't count the whole cycle. So I'm going to count the entire cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.5 divisions. 10.5 divisions. So that's wrong. So 0.05 milliseconds times 10.5 divisions. That should give us a number that makes sense. 0.05 times 10.5 equals 0.525 milliseconds. You see how this number and this number kind of jive? So in one case, we're using math to compute the period. And in this case, we're using the oscilloscope to measure the period. Make sense? You want me to do one more example with you where I don't make a mistake? Okay, let's do it. Everybody have these numbers written down in your table?
I did it through, 0.1.
Yeah. So what Corey's saying is if he did 0.1 milliseconds per division, and he counted one cycle, 1, 2, 3, 4, 5.25. So 5.25 times 0.1, you're going to get the same number, somewhere around 0.53 milliseconds. Got it? Good. Now I'm at 24.5 kilohertz. So computed period, T equals 1 divided by the frequency, 1 divided by 24,500 equals I'm getting 0.00000408. So that would be how many milliseconds? 0.041 milliseconds? 41 microseconds. So 0.041 milliseconds. Oops, wrong one. 0.041 milliseconds. What? Yeah, you can either put 41 microseconds or 0.041 milliseconds. It's the same number, right? Okay, so now we need to output on the function generator. .24 kilohertz. So I'm still on frequency. I'm gonna go 24.5 kilohertz. And now look at my sine wave. I'm going to change the seconds per division until I've got one good full cycle in there. I happen to be on 5 microseconds per division. Five microseconds is 0.005 milliseconds per division. Count my divisions. 1, 2, 3, 4, 5, 6, 7, 8.2. So 0.005 milliseconds per division times 8.2 divisions equals, that cancels, that cancels. .041 milliseconds. Isn't that handy? Because those two are exactly the same. Isn't that cool? What? For this one, for 1.9 kilohertz. Okay, for 1.90 kilohertz. Do you remember how to find, if we have a frequency, how do we find the period? Remember that formula? What is it? Yep. T, the period, equals 1 divided by the frequency. In this case, our frequency is 1.9 kilohertz. So 1 divided by 1,900 equals 0.00053. So how many milliseconds is that? This is 0.00053 seconds. How many milliseconds is it? Right, so 0.53 milliseconds. Right? Then what? This just happens to be what we're using on the scope, okay? So for this example, we need to set our function generator at 1.9 hertz, kilohertz, right? So frequency, and I'll change this to 1.9 kilohertz. Okay, so now we're outputting a frequency of 1.9 kilohertz at 1 volt peak to peak. Now look what that did to my scope. Can I read this way? Can I read one whole cycle? No, I need to change the seconds per division until I get one full cycle on the screen. Boom. All right, now look at, I got one full cycle on the screen. What is that? What is that scale now? It's at 50 microseconds per division. So now I'm looking at here and seeing what scale I have that will allow me to see one full sine wave. And mine happens to be 50 microseconds per division, or 0.05 milliseconds per division. Does that make sense? Which part? Where did I get that number? 0.05 milliseconds per division. You don't know? Okay, do you remember when my sine wave looked like this? When I changed the frequency? And you and I both said, we can't count number of divisions because we don't have one full, right? Right now, my scale right here where I'm pointing, this number, is 10 microseconds per division. That's just saying one division is 10 microseconds. Okay, so we need to change this knob. We need to change that scale until we see one whole sine wave in the screen. Do that now. Okay, now what does this number say? Okay, yours says 100 microseconds. Like, and does your sine wave look like this?
Yeah.
Okay, so we can count one whole sine wave, right? Divisions?
Yeah.
Yeah, but I need to change mine because you're on a different scale than I am, but that's okay. Did you draw this? Or did you write how many milliseconds per division on your table? Right, but you're at 100 microseconds, aren't you?
Yeah.
Would you rather do 0.05 since you already have that written down? Let's do 0.05. Okay, I want you to do this with me. Change your milliseconds per division. So it looks like that. And you should see 50 microseconds down here. Do you? Does your sine wave look like this? And right here it says 50 microseconds, 50 US. What does it say right here? Does it say 50 US? Right, but what does your oscilloscope say? 10? Does your sine wave look like that? That means your frequency is not 1.9 kilohertz. It is?
One divided by 600,000. One point six seven. You got one divided by 600,000. It doesn't matter if you use the going this one matches out. So you can't do 1.67. Yeah, it doesn't matter what unit you use, as long as you keep them all the same. Any of you moved on past that first table yet? Yeah. I'm waiting for me. Okay. Onward and upward. Blah, 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 blah. Connect. Circuit shown in figure 16-3. So we're gonna have set the signal generator for 1 volt peak to peak sine wave at 10 kilohertz. And then we've got R1 in series with R2.
R1 being the 2.7K, and R2 being the 6.8K. Okay, we can do that. Okay, so I need something, I guess I don't need that, do I? I just need to put two resistors in series with each other is all I need to do. So R1 is, what is R1? R1 is 2.7, so that's going to be the red, violet, red. R2 is going to be the 6.8. So R1, R2, and these are the probes for me. I realize some of you are still catching up on that last table, and that's fine. These are the probes from my function generator. And I'm going to hook the red up to R1. And I'm going to hook the negative up to R2. And now I have a series circuit. Set the signal generator for 1 volt peak to peak, the sine wave at 10 kilohertz. Okie dokie. Channel 1 will show some stuff. Here's my channel 1. How are we doing? Channel 2 will show the voltage across R2. Okay, so my channel 1, this is my red channel 1 from my scope. I'm going to click on there to here. And my channel 2, I'm going to put the yellow here and the ground here. Correct. You need 2 cables for your oscilloscope. Ooh. That's cool. Why do you think the yellow sine wave is smaller than the red one? Hmm? Well, it's a series circuit, right?
Yeah.
What you're doing in this, what you're seeing on the oscilloscope, we're measuring the voltage at two different points in the circuit. So here's our circuit. Function generator. 1 volt peak to peak. And 10K hertz. Right? We got a resistor here. And a resistor here. So there's voltage drop, right? Remember voltage drop? If I put my meter leads here, here, with respect to each other, what's the difference in potential? It's exactly the same as what's coming out of the function generator, right? We're seeing an amplitude over here on the red of exactly what the signal generator is getting us. So this is channel 1. And this is ground or common, either way. If I put channel 2 here, all I'm going to read is the voltage across this resistor, right? Because resistor 1 is chewing up some of that voltage. So channel 2's voltage is going to be a little less than channel 1. It's going to be the signal voltage generator minus the voltage being consumed by resistor 1. Does that make sense? Yes, no, maybe? You guys covered voltage drop first 8 weeks, right? Channel 1 will show the voltage from the signal generator. Channel 2 will show the voltage across R2. The difference function, channel 1 subtract channel 2, will show the voltage across R1. Some oscilloscopes require that you add the channels and invert channel 2 in order to measure the difference. Others may have the difference function shown on the math menu. Complete table 16-2 for the voltage measurements. Use the voltage divider rule to check that your measured voltages are reasonable. Okay, computed 1 volt peak to peak, measured signal voltage generator, signal generator voltage. Okay, I guess we can measure that with the scope. So which channel is showing me the signal generator voltage? Channel 1. And this first measured voltage is what I'm trying to find right now. Will you do that with the scope? Yeah, we can do that. We did that last week. Huh? All the commons are together on this one side.
What becomes on one side, only and these come the other two.
What?
Connect the other two on the middle and then one side.
These ones are the function generator. So I'm putting that voltage on the entire circuit. Just through the 2 resistors. Okay. Channel 1 is reading the same thing as a function generator outside to outside. Channel 2 is measuring voltage across the resistor. Okay. So all all the grounds and the commons are together on this side. Then you've got function generator in channel 1 here, positive, channel 2 positive right there. So how can I measure the voltage, the peak to peak voltage on channel 1 using the function generator or using the oscilloscope? Anybody? Anybody? Bueller? Bueller? The first block on the table 16-2, it wants us to measure the signal generator voltage. We know channel 1 is showing us that, so how can we measure it? Count the vertical divisions, right? I'm going to turn channel 2 off because the red one is showing us what we need. And then my volts per division, I'm at 200 millivolts per division. And I'm going to change the vertical position down. This is the same thing we did last week, right? All I'm doing is measuring the amplitude peak to peak. I'm at 200 millivolts per division. And if I count up 1, 2, 3, 4, 5 divisions, that gives me exactly 1 volt peak to peak. Make sense? Okay, well, what's my voltage across R1? How do we measure that? That would be channel 2, right? I'm gonna turn channel 1 off. Turn channel 2 on. Holy mackerel. Mine looks like crap. I'm gonna hit the magic button. All set. Whoa. What happened? There we go. I think turn channel 1 off. Oh. Where's my coupling VC? I want it to be VC. When I turn channel 1 off and try to only leave channel 2, it goes all crazy. So I'm just gonna leave channel 1 on there. So channel 1, I'm just putting my bottom peak on one of the horizontal lines. And then I'm gonna count up. 1, 2, 3, 4, 5, 6, 7 point. Say 7.3 divisions times 0.4 volts per division. No, excuse me, I'm sorry. Times 100 millivolts per division. So 7.4, what did I say it was? 1, 2, 3, 4, 5, 6, 7.3. 7.3 times 100 millivolts would be 730 millivolts. So how do we measure the voltage across R2? That would be computing it. But if we actually wanted to see it across the screen, in order to do that on our breadboard, we would have to flip the two resistors around, because you can't just take your channel 2 and measure across it like you would with a multimeter, because your grounds would get all weird. You would go through the channel 1 ground through your scope and back to this common. So for the sake of time, I'm just going to say we just compute it, like you said. So how many volts across R2 should it be? 270 millivolts? So it'd be 1,000 millivolts minus 730, 270 millivolts. Compute it. This is just Ohm's law. So in a circuit where I have two resistors in series, 1 volt peak to peak, so E total equals 1 volt. Total resistance is how much? It's series, so we're going to add the two resistors together. It would be 9.5 kilo ohms. What's our total current? I equals E over R, so 1 divided by 9,500. Be 105. Be microamps, wouldn't it? 0.105 milliamps. I'm just going to call it 0.000105 amps. Because I'm in volts and not millivolts, because I'm in ohms and not kilo ohms, I'm in volts, ohms, and amps. I'm keeping all my numbers the same. That's how I keep from getting myself confused. So since it's a series circuit, would the current be the same through each of these resistors? Yes. So at R1, the current through R1 would be too small to be doing this on this screen. Would be helpful if I did it on a bigger piece of paper. Okay, here we go. Do. Here's our circuit. R1, 2,700 ohms. R2, 6,800 ohms. We're trying to find the voltage across R1 and the voltage across R2. In the series circuit, current stays the same. So what I like to do in any of these circuits is have like my total values and my individual values all figured out. And in this case, we know that total voltage is 1 volt. Total resistance is 9,500 ohms. And we just calculated our total current is, what was it? 105. So the current to resistor 1 equals 0.000105 amps. The current at R2 is 0.000105 amps. So the voltage across R1, E equals I times R, right?
Yeah.
So we take these two and multiply each other. 2,700 times that number. I'm getting 0.284. So 0.284 volts. What's the voltage across R2? 6,800 times 0.000105. I'm getting 0.716. What do you get when you add those two together? 1 volt. Series circuit. So 0.284 and 0.716. Everybody good? Isn't this fun? All right, once you got the tables filled out, you can complete all the review questions and turn them into me whenever, today, Thursday, next week. A lot of you, I haven't seen your lab from last week. Make sure you get those to me. That's a great time. Good enough?